Hello, this is Chapter 8, Video 1 for Statistics. Today we're going to be talking about sampling distributions, and particularly sampling distributions of the mean. So some real quick vocab review to kind of get us set up for what we're going to be doing this chapter and the following two chapters after this. So I real quick want to review what is the difference between a population and a sample and a parameter and a statistic. So a population parameter is a calculation based on data from an entire group, an entire population. So a lot of our US Census data, we're going to be able to calculate parameters because we have data from every single person, hopefully, in the United States based off of that census. So that is a population parameter. So one example would be if I could calculate the mean height of all US teenagers. Let's say I wanted to calculate the mean height of all US teenagers. Well, that's going to be really, really difficult for me to do. I would essentially have to send out a survey or find out a way to send out a survey to every single teenager in the United States. And with a population of over 300 million, I'm sure that a big portion of that is going to be teenagers. That's just not feasible for me to do that. So what we rely on in statistics most of the time, instead of looking and actually calculating population parameters, we're going to try to do our best to figure out the population parameter based off of a sample. So a sample statistic is a calculation based on data from a sample. So let's go ahead and go back to that initial problem. Let's say that I'm still looking to find the mean height of all US teenagers, but in order to do that, I take a sample, hopefully random, a random sample from the school I work at. So a sample statistic. I would like to figure out what the population parameter is, what the mean height of all US teenagers, but I'm not able to get that. So what I'm going to do is I'm going to take a random sample from the school that I work at. And I want to talk about what that distribution looks like. So what I did was I actually did go ahead and take a sample of my high school students, and I'm going to figure out what those means are. All right, so I have a list of all of my students, all of my students' heights, and I'm going to go ahead and just take a sample. I'm going to go ahead and start calculating some means here. So I'm going to go ahead and randomize, and I'm just going to pick the first 4 students that I get. All right, so the first 4 students, let's say I'm standing outside of my classroom, and I choose the first 4 students. My first 4 students are the following heights. I have a 67-inch person, somebody who is 70 inches tall, somebody who is 66, and somebody who is 64. So if I were to add all of those up and divide by 4, I get an average height of right around 67 inches, right around 67 inches. So I'm going to go ahead and put a dot at 67 inches. So there's 61, 2, 3, 4, 5, 6, 7, 67 inches. All right. Now, that is just my one sample. Let's say that I were to do it again. I'm going to go back and I'm going to choose another 4 students. Randomize. All right, my first 4 students are 66, 66, 69, and 69. Very, very consistent there. If I were to average those out, well, think about it. Don't overthink this. If I have 66, 66, 69, 69, that mean is going to be perfectly in the center. That is 67.5. I'm going to go ahead and round that up to right around 68. So that one is at 68. So I am going to pause the video and I'm going to get a nice little distribution here. And I think you should have it in your mind what this distribution is going to look like. But I'm going to go ahead and pause the video here. I'm going to repeat what I just did several times. And I'm hoping that we can see what that distribution looks like. So I will be right back. Hang in there. All right, I'm sure you have been waiting here in suspense as to what this shape of this distribution is going to look like. It should be no surprise to you. After doing this over and over and over again, here is the distribution that I ended up with. And my goodness, this looks like the distribution that we've been working with for quite some time. This looks like it is approximately normal. Pretend that I'm drawing this nice and pretty. I'm trying my best. There we go. Yes, this is a nice normal distribution. So if I were to guess, if I were a guessing person, what if I were to add up all US teenagers, if I were to guess, I'm guessing that the true mean is going to be somewhere between 68 and 69 inches. That is where I am centered at. Now, that does not mean that every single person in the US is going to be 68 or 69 inches. And in fact, that is not the case for our distribution. And I want to talk about why this is more pinched in than a typical distribution. I'm going to go back over and look at some of my numbers here. And you're going to see some really tall people, very, very tall people. I think, yeah, I had one person this year that was 81 inches tall. Another one 74. Let's take a look. 78 inches tall, 76 inches tall. This is well over 6 feet tall. This is 6'6". And then 6'9" down there. There are people that are taller than that. However, this isn't saying that just one person is 74 inches. That's saying that I randomly selected 4 people and those averaged out to be 74 inches. There's somebody that's at 81 inches, but there's no possible way that we could add up 4 people's heights and be all the way up there. Now, my shortest person in here, I believe, was 59 inches. Let me see if I can find it. I remember I thought I had a 59 in here. It's like the where's what? Oh, of course, it's the last one. I did have somebody who was 59 inches, but that would be all the way over here. Looking at the data, yes, there is one person that is 59 inches. However, in order to add up 4 different people and have those average out, we're not going to have an average of 59. So the more and more people that you sample, the tighter it is going to be. So I'm going to go ahead and write that. The larger sample you take, and I'll go ahead and say tighter the distribution is going to be. Now let's go ahead and turn those into mathy terms. If I'm talking about the stretch of a normal distribution, that means that my larger sample is going to be a smaller standard deviation. So the larger my sample, the smaller my standard deviation is. So if I were to have just a sample of 1, I could have all the way to 59 to 81. But in this one, I had a sample size of 4, so I'm going to have a smaller standard deviation. So in comparison, let's go ahead and say that we were to take a population, let's go with, just compare some things, or a sample. In this one, we had size n is equal to 4. Let's take a look at what would this be compared with a sample of, let's say instead of 4 students, I were to take 20 students. Well, if I were to compare these two, my sample of size 4 is going to be like that, very similar up here, but a sample of size 20, that is going to be much, much tighter. More likely, those are going to all fit into that mean. It's going to be very rare for us to spread out. So, a few formulas for you guys today. I'm going to go ahead and go over one example problem, and then you guys can get started on your homework for video number 1. All right, so let's go ahead and talk about a few different definitions today. All right, so we are talking about a sampling distribution of a sample mean. All right, so let's go ahead and talk about what this is going to be centered at. So my center, the sample mean of my sample is going to be centered around what the actual population mean is. So this is going to be centered at that population mean. So this is going to be centered at the same mean that we are expecting. All right, now let's talk about our standard deviation here. Our standard deviation for this distribution, our standard deviation of our sample mean is going to be the standard deviation of the population divided by the square root of n. So yet again, this goes with what I was saying, that bigger bigger sample that you take, the smaller the standard deviation is going to be. All right, so I'm sure this means absolutely nothing to you right now, so that's why we're going to go ahead and do an example here. So here we go. Here's what we're expecting our sample to look like. All right, so here's our example down below. The birth weights of newborn babies in the US follow a normal distribution with a mean of 33.4 kilograms, 34 kilograms, that'd be huge, and a standard deviation of 0.6 kilograms. Researchers interested in studying how children gain weight decide to take a random sample of 100 newborn babies. And then they calculate the sample mean birth weight. Calculate the mean and the standard deviation of the sampling distribution. All right, so let's go ahead and take this mumbo jumbo and actually draw into something that we are comparing it to. All right, pretend that that is symmetric. All right, so with our sample of 100 newborn babies, I'm expecting these newborn babies to be exactly like the ones in the regular population. So if the typical population is at 3.4 kilograms, I'm expecting this to be centered at 3.4 kilograms. All right, so I'm expecting this to be 3.4 kilograms. All right, but what is going to change? I'm not selecting one baby, I'm selecting 100 babies. So this is going to be much tighter. This is going to be much more condensed than a typical distribution of this. So let's go ahead and take a look at our standard deviation. Our standard deviation is going to be, typically we have a standard deviation of 0.6 kilograms. So 0.6 kilograms. However, we are taking a sample of 100 newborn babies. So this is going to change this. I'm going to divide by the square root of my population, or my sample size is going to be divided by the square root of 100. 0.6 divided by square root of 100, well, that's just 0.6 divided by 10. My new standard deviation is going to be 0.06. So between what I'm expecting and my sample, the mean is it's going to still be centered around the same weight. This sample of babies isn't magically going to be heavier or lighter than the other babies, but the only thing that's going to change here is that standard deviation. All right, so I know we went over a lot. Real quick recap. A sampling distribution. We usually cannot calculate population parameters, so we're going to have to rely on samples. Now, every time you take a sample, it is going to be pinched in a little bit based off of your sample size, your sample mean. So the larger the sample you take, the tighter the distribution is going to be, but they're still going to be centered around what you expect. We're expecting heights of 68.5 inches for a mean. That should be what these are all centered around. Those are going to be exactly the same. And then finally, for some actual calculations, down below we looked at, hey, we're expecting it to be centered around the exact same mean that we're expecting of all babies. The only thing different with our sample is our standard deviation is going to change. Hopefully this helps out. Please let me know, send a screenshot if you have any questions, and you should be ready to do video number 1 homework. Have a good day.